I don't think so. It just wants you to practice like yeah.
Right here it says when a signal orbital is occupied by two electron posits, so it's also a signal line. What's a signal orbital? That's just
Yeah, so that's just when they come together. Yeah, so that they're like in favor, right? So when you can come together, yeah, just any signal.
yeah, and then the signal.
Yeah, yeah, so that's just remember anything kind of reaction is the signal.
Okay, and that's
Oh, yeah.
This is where we can start.
Yeah.
Oh.
Not incorrectly, but does this one just have one set? Or there should be two sets, right?
No, it's fine because it's the PZs, because right, it's just PZs coming together, so yeah, it's just one, because you don't have the two degenerate ones like there.
Okay.
Yeah, because the other one is the anti-bonding combination.
Okay. That makes sense.
MO? Molecular orbital? What we've been doing. So yeah, as you get settled, practice, right, drawing our MO diagram. This is basically your homework too. Look back at your notes, right, your generic A2 with SP mixing. You could also kind of reference this, although, right, it does tell us the answer, but we want to practice just kind of drawing it, right, deriving it. So I'll let you keep working on that. you should only have 8. So keep taking a few minutes, but again, you probably want to be referencing something. So I'll pull up our A2 here so you can look at that. And again, double check yourselves. You should have 8 MO mixed in the middle. So 1, 2, 3, 4, 5, 6, 7, 8. So you really want to make sure you get the order though. So not just all the lines, but the order of that. And again, just kind of understanding where they came from. So kind of keep working on that. Again, right, reference something, help yourselves. But then, right, you want to redraw this so you're understanding what orbitals are coming together. Well, you got, looks like you have 5 and 5, right? So that's 10. So yeah, we just need 10 in the middle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 should be the last one. So yeah, that's pretty good. Because right, even though it's anti-line stuff, it's still like that, because it's 1, 2, 3, 4. So this is a 2S, right? I mean, this is a 2S anti-bonding, right? So you gotta fill that there, because it's still mixing energy. So even though it's anti-bonding, it's still gotta fill it. No, you always fill from the bottom. Yeah. No, you just fill them in order, because this order, how you draw them, is the energy. So they should already be from lowest to highest. That's the point. And then, yep, yeah. Yeah. Yeah, and then just double check this, because you got the order swap. So this looks like the non-mixed diagram. So remember, when you mix things, you just have 1, 2, and then the P is mixed. And the 2 degenerate pies, it does a weird switch. Yeah. Yeah, so you gotta swap them. You need the degenerate pies down here, and then the S. So yeah, you might want to reference your textbook or something. Or, I mean, it's up there too. Yep. Yeah, exactly. And is this one, this switch or, the switch is, here that switch, but yeah, you have to switch like here, and then yeah, it's here, the other one is back lower, back there. But yeah, this is like, valence electron is 7, and this one is 10.
too, like, what's the version? Yeah, version is, yeah, especially for this one, you want to reference the chart. I don't expect anyone to memorize this. Yeah, so that's what we want to do initially, and we're just going to redraw it and understand what the color always like. Yeah. Yes. So we have, yeah, the second two is, oh, this one, sorry, they just have it in a different order. So they don't show any mixing, so this is just a 2X, this is 2X just pure M1, and then this is the GM here. So that's what's weird about this, is there's like no mixing, it's showing you the two same orbitals. Yeah. Yeah, and then these are degenerate, right, so you can't get any of these go up back. Oh, sorry, no, I just, yeah. Yeah. Yeah, they're degenerate pylons, so they're, right, the X and the Y free space.
Yeah.
So that goes back to that mixing argument here. So basically,
See if I have it on here. Because we made it like non-bonding, right? So this is what it is. So it's essentially non-bonding is how I called it, because we moved the electron density to the outside. So that's where the degenerate p orbitals actually have better overlap, right? Even though it's through space, we don't have a lot of electron density in that sigma bond, as suggested from the mixing. All right, so the diagrams were looking better as we spent more time staring. And so again, right, just kind of continue to stare at these until they really make sense, right? Again, I don't know if I should print this out maybe as a cheat sheet for y'all. That might be an idea. I could print that out during the break or during your quiz time, right? So this is basically our cheat sheet, right? Or you could either have, of course, right, we have our blank frameworks. These are our cheat sheets. So obviously we had done O2 prior with no SP mixing. Then we left off on Tuesday, right, with our SP mixing. And then just going back to this, right, again, it gives us the answers, so to say. And again, emphasizing that oxygen, fluorine, and neon, we're not invoking SP mixing. Again, just due to the difference now in the p and the s orbital, right? You can even see it in this illustration almost, so you can see how close, right, this p and s is versus as it even gets, right, a little wider further down. And so I'll just redraw it for good measure, because again, good practice to just kind of do it over and over again. And so I saw really good setups, right? We had our nitrogen looking at our valence electrons, and most people again set that up for success with our 5 valence electrons. And then it was just trying to remember, or again, I don't expect you to remember, so I've been drawing MO diagrams a long time. But right, reference this, use this on an exam, right? That's, I want you to use this. This is again, right, basically like the whole chapter right here in a lot of ways. And so just practice, okay, just like before. And if you can recall, right, we had mixed them to get that really favorable interaction with the electron density in the center from our sigma bonding. And then, of course, right, we had our anti-bonding combination, which we were able to at least minimize that anti-bonding interaction, right, by having less electron density in the center from our SP mixing. And so that's formally anti-bonding. And then again, don't forget that's where we have our switch. So I'm just referencing this. And so good question about it. And I just wanted to kind of go over again the order. So what happened when we had done this mixing? Remember, we had these two bonding interactions, but then the 2s and the 2p themselves were out of phase, kind of leading to this area, right, of less electron density. So because there's less overlap, this is higher in energy, and actually, right, those p orbitals have more favorable bonding overlap. So that's why they're next. So there's, right, the switch. Yeah.
Is the property of anti-bonding defined by the basic symmetry or the electron density concentrated on one side?
Sorry, I feel like your question, it's kind of twofold, right? So that's why we invoke SP mixing, right? Because maybe we can do something like this, right, where we can put the electron density on the outside, which does make it kind of more favorable and drops the orbital. Does that make sense?
So if that anti-bond was drawn with the dark parts on the outside, like what's on the inside, would that be the bond?
Yeah, so that's this non-bonding orbital right up here. And it doesn't matter, again, the shading, just that small electron density, right? Shading matches, so then we're saying electron density is more on the outside, though, for that orbital.
So the one on top is a bonding orbital?
Yeah, so this one, right, is still formally bonding. So when we're writing this, right, it's still a PZ sigma mixed, right, orbital. So bonding. So still bonding, so you still count it as your bonding. But again, right, just thinking about where the electron density is, it's going to be on the outside, right? So these are probably where your lone pairs are, is kind of what we're getting at as well. Or at least they'll be there. And so I'm trying to show the MOs. So I have, sorry, a little slow. So I was just looking at another website that again has our MOs so we can kind of see it. And so again, this is the one we are talking about. So where our electron density is minimized. And so this is actually what we get, right, from our now computer calculation of, again, our density map. And so we're seeing, right, a small ball in the center. So again, right, even though it's formally bonding, right, and you can kind of see that, right, we have this sphere between the two showing our bonding. But again, we've minimized that electron density here. So really, right, your electron density is going to be on the outside. So that's what that's showing.
It's essentially, it's less that the electrons are attracted to each other, but they're repelled into each other.
Yeah, well, it's like where they're favorable, right? Because you have to think about what the orbital means, right? Because your orbital is just telling you, like, where is it probably going to be? And then as we do these mixing things, it's still just like a probability density map that we're ultimately getting at. So yeah, we're saying like, okay, when we have electrons occupying this orbital, they're going to be hanging out in the outside space more, right? So even though they may be zooming through the middle as they run around or whatever, it's still going to be just on the outside.
Does the base of the diagram correspond to this kind of
So they've probably have to be, right, like in phase, so they have to be opposite spins to pair. So it doesn't really correspond. It's just more like, again, favorable interaction versus not. All right, so then continuing, now we start getting into our antibonding. So now we can make, right, our P antibonding. So PX, PY, pi antibonding. And then double check yourself, 1, 2, 3, 4, 5, 6, 7. And that leaves us with 8. So we said, right, that really bad combination. And so that would not be favorable, right, an antibonding orbital where they are occupying that middle. So obviously, right, that would not be favorable, just kind of like we saw with helium. So obviously that would be why diatomic neon does not exist. And then fill in our electrons. So of course, 1, 2, 3, 4, filling them properly, 5, 6, 7, 8, and then 9, 10. And so now we can say, right, this is our HOMO. So again, highest occupied molecular orbital. This would be our LUMO then. And again, that's lowest unoccupied. And so again, just kind of thinking, right, how you can extend this, where we're going. If you're saying, right, that nitrogen is donating an electron, that you're probably looking at the HOMO, right, and looking at that pair of electrons. Or if it's trying to, you know, do something weird and do some sort of like pi back bonding, accepting electrons, then you'd have to look at the LUMO. But that starts getting into other things. But again, just trying to set you up for the future. Are we on time? All right, so let's just kind of recap, right, with kind of our previous examples that we've been looking at. So remind me, what's our hybridization on this one? So SP, so good, right? And then it's showing us, this is kind of confusing, but it's trying to draw how you get like your two, well, basically, right, it's saying that this plus this equals basically that, right, our SP hybridized orbital. So it's trying to show you the math behind it. And then again, just re-emphasizing the bonding. So we can again see, right, we have this SP hybridized orbital, just like before. And then, yes, right, there's our, we'll call this PX, PY, right, still available since they're not involved in this SP mixing. Just like before, right, we just have our 1s for hydrogen, sigma bonds, like it's pointing out there. And then, right, just showing the difference. I think some people were kind of asking about this for fluorine. And so, right, I was kind of just showing it as a point charge, but now we can kind of see, right, obviously our fluorine has our, all its orbitals occupied, and then it just has our 1 electron, so just our 2p, in this case, right, our z orbital to interact. So of course, again, right, sigma bond, and then right, beryllium still sp hybridized. And you could again go back and think about this. So right, our fluorine atomic orbitals, just kind of so we're clear on this. So of course, 2p, 2s, 1, 2. And so, right, all of them are of course occupied, just leaving, again, whichever one you want to call it. So they just labeled it 2p, right? I'd call it 2pz, but just showing us, right, that's the one that's available for bonding. It just has one electron, so therefore it can, again, make that sigma bond with beryllium. So this is just beryllium F2 for clarification. But again, right, it's okay to just simplify our fluorines or any halogen as a point charge as well. And so now, again, just kind of going through, what's this hybridization again? Oh, it tells you, sorry. But what is it? So sp2, so again, just kind of recapping and reminding you, and they have pretty pictures, unlike my terrible drawings. And so, right, they called it PZ, X going into it, and then, right, just showing there's our PY that's still available. And then again, showing our orbitals for our tetrahedral. So there's, right, one sp3 orbital, and then there would be 4 of them, giving us our, of course, 4 lobe thing that we're used to seeing. And of course, again, now all those orbitals are mixed. And so let's look at some other, is this what I want to look at? I think that's pretty, again, self-explanatory. So what's our hybridization on our carbon here? Oh, count one more time. So it is tetrahedral, but then what's the sp3? So right, each carbon center is sp3, so that tetrahedral geometry is another good giveaway. Well, it's just going to be a S, right? So it's always just like a sigma on. And so again, right now it's showing you our sp3 hybridized lobes. We can see how, right, 2 of them come together, so we have our sigma bond there between our 2 carbons. And then, right, the rest of those electrons go into bonding with hydrogen. Yeah.
Yesterday you said that the orbitals like are positive and negative, but it's just like not really.
Yeah, so that's how they show the shading, right? So whether, so basically what we're saying is, right, they're in phase to come together to make a bond, right? Because you have to have them in the correct spin states so that they can, right, be together. So basically when we're saying that they're positive, it just means that they can come together. Or again, they're the same color, whatever. But yeah, your textbook uses that plus minus notation. So yeah, in this case, we're not trying to show that there's a bunch of plus charges everywhere, but rather, right, they're in phase or bonding. Kind of confusing. And again, right, just a bunch of sigma bonds. Just so we're clear on that. Let's look at some more things. So we got our double bonds next. And so again, like we saw, what are we looking at here? Oh, this is, sorry, ethylene. I couldn't even tell what my notes were. So this is showing here ethene. So our double bond. And what's our hybridization again here on this carbon? sp2. So both of these, right, are sp2. And so I think people were already starting to do this last week, but again, you're kind of thinking about what does it look like. And so why I kind of like this baby kit, as I call it, is, you clearly have, oops, sorry, I had a few non-sp2. So right, I can pass this around. So this is planar, right? So again, we're kind of seeing that this is an sp2 carbon. And so right now we're thinking, okay, that means that this structure, right, is planar. Versus, so again, sp3, that has more 3D character. So I'll kind of pass and build. Yeah, and the hybridization, right? So like, yes, you have the double bonds, but it's kind of like a twofold thing. So I'll pass this around so you can just kind of, again, compare those structures. Because that's like the next hardest part of OChem is like, is it flat and therefore it can attack like on any side? Or does it have some shape? Is it going to invert the chirality? So that's why you want to be thinking about, is it planar? Does it have 3D shape? And again, right, I'm just trying to set up our foundations here. Yeah, so it's a couple of things, right? So we have just being sp2 hybridized, right? That gives us that planar shape, right? But then, in addition, which we're kind of getting to, is with this double bond, right? So we have, now we can kind of look at their plus minus thing for this case. So, right, if we have our favorable interaction up top, right, and this is negative, whatever, favorable in phase on bottom, what we're saying is with the double bond, we can't have rotation. And so you'll find that out in OChem. So no rotation on the double bond. And that's exactly from what you said, right? Because now if we try to rotate it, they would obviously be out of phase, right? So that wouldn't, we would break our pi bond, so.
The positive and negative phases correspond with favorability.
So anytime they're together, it's just because I don't draw shading, right? So how I would draw it, that's why I don't like the positive negatives. Because remember, each pi bond, or each p orbital, already has a node, right? So that's what's being shown here, with the positive and the negative, is those nodes. So I would draw it as a shading, again, not showing charges. We're just showing these are in phase, so they have a pi bond.
And is it implied that the sigma bond is centered negative?
It just is a favorable interaction, right? So I wouldn't read positive, negative. I would probably put it a positive, right, with their little notation, because you want to say positive to show that they're in phase.
And that there are no negative phase sp2s.
Yeah, so they're all just like, we don't want to get too complicated with it, but yeah, they're all just like shown right now as point charges. We're just assuming that they're all the same color and then will therefore bond with the hydrogen. And so again, right, so if we have our double bond, we're again just re-emphasizing that means we have our sigma bond, again from our sp2 interaction, right? So sp2 overlap. And then we have, right, our pi bond. And that's only because, right, we have an available p orbital as well, right? So if the p orbital had been involved in the hybridization, then obviously, right, we wouldn't have anything to make a pi bond from. And so then we can just kind of draw this out for formaldehyde. Just trying to get through it. So again, right, our sp2 hybridized on there, on our oxygen, and also on our carbon. So again, right, this is telling you planar structure. So you can just think about that. I won't go over all the orbitals, right, but again, we can see we're also going to have our pi bond. And so like we had mentioned, because we can't rotate that double bond, this is what gives us different isomers as well for these double bonded species. So we have this trans species versus our cis isomer. And so then, right, quick recap of our triple bonds. So now, right, this is this complex or cyanide. And let's see, again, sp2 hybridized, or excuse me, not sp2, sp hybridized, right, leaving us with, we'll call it px and py for our 2 pi bonds now. Oh, and I swapped my axes accidentally, sorry. And so again, just seeing that. So let's look at benzene over here. And so benzene, this shows you, this starts to get into like more advanced stuff. But basically, so let's back up for a second. Let's draw out benzene and not just looking at all its MO combinations. So benzene, if you remember, is a 6-membered ring thing. And it could be drawn like that or abbreviated like that if chemists feel super lazy. And then let's draw it out explicitly. So all it is a sp2 hybridized ring structure with these alternating double bonds. But as you can see, right, you can rotate these double bonds around. And that's what leads to what's called this delocalized pi system. So now we've drawn it out like this. So again, right, each carbon, I'll highlight them all. So every carbon is sp2 hybridized. But then that leaves us, we'll call it py. And so now I'll draw what we're essentially looking at. Sorry. And so what we're looking at is, again, our pi delocalized system. And they will be delocalized when they're all in phase. And so this is, right, the in-phase combination. Again, this is mathematically speaking with symmetry and no nodes. And so, right, again, we have this delocalized system, so that means we have pi bonds, right, all the way around and obviously on bottom. And so all this means is our electrons, and that's why we draw it as this little ring here. But basically, these electrons run around, and that's a pretty favorable system to have this pi resonance. And this is called an aromatic compound. So when we have a ring, that means that it's aromatic, which again just refers to the localization. And then what's shown here is just the mathematical combinations. We don't really need to get into it. We can just appreciate it. And this goes into like bonding, other bonding stuff and how it can bond. So we're getting there. So right, the first one we mentioned had no nodes, and that's the most favorable one. Again, that's the one we mainly talk about. But then what it's just showing us, so again, we have 1, 2, 3, 4, 5, 6 p orbitals. That means we're going to get 1, 2, 3, 4, 5, 6 mathematical combinations of basically our orbitals. And so what it wants us to appreciate, so we have these things called nodes, and it's basically how you can slice it. And so this node goes across these two, so it's irrelevant what the shading is on here. basically what we're saying is it doesn't matter, right, if it's that way or the other way, because either way it cancels out by the node. And so what we're looking at on this node is there should be a pi bond though there. So again, with its little plus minus notation, right, it's saying they're both negative on top, so yes, they're pi bonding. And then this side, right, so the node now makes them opposite. So now they're opposite sides of the node. And so now they're positive on this side, but again, still pi bonding. And I don't know if it's worth me drawing it, but basically something right like this. And then this just has the node drawn the other way, but now if you draw it the other way, there's no p orbitals right lying on the plane of that node. So we just have, again, one side flip one direction, and then the node indicating they have to be opposite. So again, like so, kind of sketching quickly. Yeah.
In the first diagram you drew, the nodes at which they're going to work was assumed to be occupied by another.
Well, we can't assume anything about occupancy yet, right? So we're just kind of setting up, these are just mathematical combinations.
So on B, how come like with those I'm getting like there's a section in the middle of
Oh, because, well, we would have to get into symmetry, but basically what we're trying to overlap with is, let's say we're trying to bond with something that looks like this. This is where like the next step is going, right? So you want it to be dark shaded over here so that they all match, and light shaded over here so they all match. But then these are right in the center, right? So they're right in between the dark and the light, so it doesn't matter if this is dark or light, it can't bond. Does that make sense?
And then the C kind of is looking like if one looks like one way, the other looks like the way, or if both is like a 4
Depending on the alignment of the pi bonds, we're going to match in one direction.
Well, yeah, so this is where we get into symmetry, because I'm telling you, right, they're not going to match there. That's why we have a node. Because, right, we're saying that if this is dark, it both matches with this one and doesn't match with this one. So it's irrelevant, is what we're saying. Yeah, but this gets into more math, and how to like really explain it is to get into the symmetry elements more, which we don't want to get into symmetry in this class. So I'm trying to wrap this up. So, right, you can just see how we can continue. So I'll just kind of abbreviate this. So now we have two nodes. And again, you can see, right, where every time there's a node, the shading flips. But then, right, it's either, so in this case, these two still have a favorable interaction. Right, this one is all flipped. These two don't matter. And then obviously the craziest one is going to be 3 nodes, and basically they're just alternating, right? Up, down, up, down, up, down. So no really, right, pi interactions here, since they're all opposite shading. All right, moving on, last little bit. I just wanted to talk about, again, some oddities, some weird stuff in OChem that will help you now. Again, right, just kind of appreciate it and take it in. And so, right, there are some funny things that can happen in OChem. And so kind of looking at this, because nitrogen is always funny, and this is always good to think about, because you should, again, what we're trying to get at is like, well, what's the reactivity, right? What can happen here? Is this susceptible to attack? And so if we look at this, right, we're just looking at this, it would be easy to assume that it's sp3, right, because it's attached to this 1 carbon, 2 hydrogens, and it's got this lone pair. But what could happen, and what you, again, want to consider as you potentially go on in your chemistry career is, well, what's favorable? And so what we mean by that, and let's kind of draw this out over here. So we have this system here with our nitrogen. And so what we want to happen is we want to have, right, some sort of p orbital interaction. So let's kind of think about what's happening on this carbon, right? Before we even fully dissect this nitrogen, let's look, at our carbon. So what's our hybridization of our carbon there? So sp2 again, so good, getting faster. And so right now we're just kind of thinking about what that looks in general. So obviously our sp2 hybridized. But then we're saying, well, we do have, right, an available, I'll call it pz today, pz orbital, right, again going up and down. So again, we have to kind of think about our structure. So this little, I'll call it our formate piece or whatever, our carbonyl group. So obviously, right, that's sp2. So now we have our p orbital going up and down. And so now if they want to interact, basically they have to be in phase, right? They have to be the same. And so now what we're saying is, again, let's go back to our expected, right? So now we have, if we had our sp2 carbon here, again, it has our pz there, as we're calling it. If our nitrogen was indeed, right, sp3 hybridized, yes, it could bond like this, but then it would have this lone pair, right, and this sp3 hybridized, but it's not prime, right, to pair with that pz is what we're saying. So basically no pi interaction. And so that's why it doesn't do that, essentially, right? So it actually wants that pi interaction. And so what you actually find is, okay, so the nitrogen is actually sp2 hybridized. And so, okay, those hydrogens are hanging off over there, sp2. But then what does that mean for our lone pair? Well, that means that our lone pair can hang out in our pz now. And now, right, we can have some pi interactions here, which means we can have some resonance structures.
So the px, py, pz line the same within the molecule? Or are they always using the same coordinates?
Like within the molecule itself, but again, you can assign, right, any coordinate to any molecule. You could call the principal axis, you know, y or x. It doesn't matter. You would just, I mean, we usually just do x, y, z coordinate system. It'd probably really start to confuse people. But okay, because again, they're now in the same pz orbital, right? So again, they're both now pz's. Now they can interact. So what this means, and so now we can draw this out, what's going to happen, or what can happen, is, so then, right, we can draw resonance structures where we can take this lone pair and, right, actually kind of make that bond. So then we'll make that pi bond. But then that'll kick this up to here. And so that's always favorable when you can kind of move electrons around, right, get reactivity. And so then, right, we'd make something like this. Make sure I have my charges. Oh, negative charge, sorry. And so this just means, right, you could get reactivity here then. So, and again, resonance structures. And so electron movement. And so that's also what you're looking for, is like, it has to be sp2 hybridized if you're going to go ahead, right, and move these electrons around. Does that kind of make sense, what we're seeing? Because otherwise, if it's not sp2 hybridized, right, we can't make that double bond here, is what I'm saying. So if it was sp3 hybridized, that would not happen. And again, these are kind of advanced concepts, so just kind of try to take it in. And again, same thing with this system. So we're kind of seeing something similar, right? That sp2 hybridized carbon. So again, it's going to have, we'll call it again py. And so that's kind of why this nitrogen again wants to be sp2. So again, you can move those two electrons around. And so same thing here, right? This is a funny one. So again, this oxygen, we expect it to be sp3, right? This looks just like water almost. But because we have this sp2 carbon here, it's actually more favorable to do sp2. So again, we can have that pi system. So again, similar example here. Again, your hint is, right, it's near this double bond. So it wants to be part of that pi system.
What differentiates the velocity of
Yeah, I think they are. Well, this one's like a carbonyl group versus just a sp2, right? Yeah, but just like you noticed, still just a double bond. And then same thing. So going back to aromatic systems. So again, thinking of how we can make it aromatic. Well, it has to be sp2, otherwise that would break the aromaticity, right? So if it was sp3 hybridized, then it wouldn't have a p orbital to be all delocalized with, and so it would not be aromatic, right? So again, you're kind of thinking of, yeah, we have to make this delocalized pi system, and in order to do that, we have to have an available p orbital. So again, that's why those end up being sp2 in those cases, so kind of weird.
So cool. How do you, you said the M is negative, and then that's number of bonds times 3.
Sorry, what? I missed the question.
On the first, the one that you're drawing that hand.
Oh, when I like
Yeah.
drew the charges later?
Yeah.
Yeah, so then, right, I just drew in the formal charges
And the equation
is valence electrons. So I'll write it here. So formal charge, it's just the valence electrons right from the periodic table minus the number of bonds individually, and then minus number of individual electrons. So right, 5 minus 1, 2, 3, 4. That gives us +1. And then we could do that for oxygen. So 6 minus 1, 2, 3, 4, 5, 6 minus 1 bond, so -1 there. But yeah, I do that pretty fast. What? Sorry. Oh, number of electrons. And yeah, individual electrons, so count them. All right, so I think then the formula would be 2 times the electron pairs. That's why I say individual electrons in case you have a radical. Yeah, so electrons is like attached to it. And then, so I think that's pretty much the end of lecture. And so, right, we'll take our 10-minute break. We can do our quiz, but again, just take it in, right? Try not to be overwhelmed. I don't want anyone like freaking out or anything, but just, right, take it in. Take in the little structures that are going around, right? You want to really see, okay, what's sp3 versus what's sp2, and that really like goes a long way, right? What's planar, what's 3D. All right, I'll let you chew on that and have a break. And yeah, let's give ourselves 10 minutes, so probably start the quiz around 12:05, although I can hand it out. So I'll hand it out, but I don't know why I said it.
For that.
Yeah, to be able to like do the resonance structure, because otherwise that lone pair is kind of trapped, hanging out right in an sp3 hybridized.
What makes
Because, right, so then it's occupying that PZ, and so that can happen just like naturally residents, you can just draw those resident structures, like those kind of exist. But then, when you go into OChem, you're kind of looking at like points of attack, so that's where you're like, okay, if I can go on a resident structure, yeah, I can do something. Oh, yeah.
Oh, she's at the back.
Oh.
I can.
Screw it. I feel like most people finish like an hour early.